Anybody have an
You might find some over the microwave. Yeah, I'm not a fan of caffeine either. Okay, ladies and gentlemen, here we go. The sooner I finish, the more time you'll have to work on your own stuff.
Yes.
I know. School is where kids go to watch adults work. If you went to a store and bought some ice, yeah, we actually talked about this briefly earlier. If you went to a store and bought a bag of ice, do you think they leave that bag of ice at 0 degrees?
No.
Why?
Because it doesn't.
Exactly. It wouldn't. If it was 0 degrees, it would start immediately melting. So they usually keep it at about -20 degrees. So you got that. Yeah. So you got that bag of ice, and you put it in the car, and it's like it's a hot Southern Nevada day. What immediately happens to that bag of ice? Yeah, it starts warming up. It doesn't actually melt because the melting point of ice is what temperature?
32 degrees Fahrenheit.
Fahrenheit's a bad word in here.
0 degrees Celsius.
0 degrees Celsius. So the water has to get to 0 degrees Celsius first, and then it'll start melting. And something really interesting happens. During a phase change, the temperature is constant. So during a phase change, the temperature is constant. So we're going to start. We got our. We went for that. There we go. Okay, so we got our ice at -20. It's going to start warming up, and while it warms up, while it absorbs heat from the environment, it starts warming up. Now, once it gets to the melting point of ice, 0 degrees, it starts melting. And what's interesting is all of the energy that it takes from the environment goes to melting. So if you stuck a thermometer in that pool of ice water, it would be at 0 degrees. Because all the energy goes into the phase change. Now, the temperature change, gotta fix that. The temperature change is what you know. When things change in temperature, it's MC delta T. But when things go through a phase change, it's just mass times a phase change constant. So it doesn't have a specific heat constant, it has a phase change constant.
And that's the L. The L is the phase change constant.
Yes.
Wait,
yeah.
Write down.
So again, the important thing is during a phase change, the temperature remains the same because all of the energy goes into the phase change. Now, once that entire bag has turned into a liquid and it continues to absorb energy, what is it going to do?
Temperature's going to rise.
Temperature's going to rise. And what's the graph going to look like now? It's going to go up diagonally again, right? So again, we're back to the MC delta T because it's warming up and warming up and warming up. And then it gets so hot because it's crazy, crazy hot. It gets so hot in your car, it's over 100 degrees. Ah! Maybe you parked in just the wrong place. And everything in your car is like 100 degrees Celsius. What's the water going to do?
It's
It's going to start boiling. And with what you know about phase changes, what's the line going to look like?
Straight
It's going to be a flat line again because all the energy is going to go into the phase change.
Wait, so what do we put as the question mark? Just a question
This
mark?
is like, the question mark is just like, hey, ask a question.
Oh, so what was the answer?
Yeah, exactly. What happens now? So warming, phase change, and then if somehow your car gets above 100 degrees, after all the water has turned into gas, then this line just goes, woo! It just keeps going until it becomes a plasma. Highly unlikely that water in your car will turn into a plasma, but it just keeps going. So horizontal line means all the energy during a phase change goes to the phase change. Diagonal line means energy going into the material causes a change in temperature. Again, temperature is on the y-axis, so if we have a horizontal line, the temperature is constant. As we add heat, temperature is the same. Waiting.
How can water get colder than 32 degrees without freezing, or 0 degrees Celsius?
It is frozen.
I know, but I swear.
Oh, how can it?
Yeah.
It goes to what's called a supercriticality. Okay, so supercriticality is what happens when a material wants to change phase, but needs something to get it started.
Is that when you like you freeze your water bottle for like 2 hours and then you hit it and it just like freeze like?
Exactly right.
Yeah.
So some materials, water included, can basically become supercritical where they should undergo a change, but they need something to get it started. That's the thing in the water bottle on the table. So that's just called supercriticality. Yeah, it just happens. It's really cool when it happens in nature. You get all sorts of funky stalagmites and stalactites. But anyway, moving on. Okay, if you are ready to move forward, give me a thumbs up. If you have questions, wave your hand around.
Wait 2 seconds.
Wait 2 seconds.
What is the question marks? For the second,
Like what is it?
Like,
Gas
what is
plus heat means
equals
temperature change.
temperature change, and then is the phase change.
Yeah.
And then the liquid and heat is temperature change.
Cap gun.
Yes.
Okay, I got it right actually. Give me a thumbs up.
Give him a thumbs up. Wait, ratings are
We get liquid.
All right. So here's a fun word, enthalpy.
enthalpy.
This is a pretty important word, and it basically means heat. We're going to find that there's various types of energy, but enthalpy is not so much a type of energy as it is a name for heat that goes into or out of a system. So the enthalpy of a system is the heat energy, that's weird, heat energy that either causes a change or is the result of change.
That's slightly confusing because it's delta H.
Yeah.
Enthalpy instead of delta Q being heat. You know what I mean? Why did they do that?
I wasn't in the room when it happened. I don't know why they do
Did
that.
you go flat?
Well, they're all dead, so that might be hard. I wasn't in the room when they did that. So again, just remember that delta H this is going to be a variable we're going to be using later on. The upside is it's heat, so at least it's an H, right? Okay. So enthalpy is delta H, and the reason it's a delta H, what does delta mean? Change. The reason it's a delta H is it's a difference between where the system started and where the system ended. Okay, you have to have it's what's called a state function. It's between where it started and where it ended. Now, sometimes systems require heat to move forward. That's called endothermic. This is a word you learned 4 years ago and also last week. So endothermic requires heat to go, or exothermic, it releases heat as it goes.
Oh.
So again, the delta is important, it's a change in exothermic reaction. An exothermic reaction, again, releases heat. And that means that delta H is negative. If you observe heat coming at you, the system is releasing the heat. It's delta H. If you observe heat going into the system, then we call it what?
Endothermic.
Endothermic, and endothermic has a positive delta H.
So basically, enthalpy is just heat in motion or in action.
It is the difference in heat between where a system starts and where a system ends.
And then exothermic is heat leaving.
Heat leaving the system. Yeah.
leaving
So,
the system.
If a system starts with 100, I'll go ahead and say kilojoules, 100 kilojoules of heat,
Yeah.
and it ends with 120 kilojoules of heat, final minus initial, 120 minus 100 is 20. That's an endothermic process. On the other hand, if a system starts with 100 kilojoules of heat and ends with 60 kilojoules of heat, final minus initial, 60 minus 100, then the delta H is negative 40 kilojoules per mole.
So exothermic heat is leaving the system.
Yes.
Makes sense.
Yep, endothermic is going in.
I'm having a hard time grasping the difference between enthalpy and heat.
At this point, there isn't one.
Oh.
The only reason it's a different variable is that physicists like to use Q.
Wait, that enthalpy.
So heat.
So the Q you used for calorimetry
Yeah.
was enthalpy. It was a difference in where the metal started and where the metal ended. It just wasn't listen carefully, It just wasn't a physical change or a chemical change that occurred. So when we're talking about enthalpy, there is a specific change that happens. So you can think of Q as the heat energy that just warms something up. You can think of delta H as the heat energy when a very specific thing takes place, like melting or boiling.
So like, what's an example of heat in the system? Like something cooling down.
Yes, or something freezing. So in order to freeze, like you put a cup of water in your fridge or your freezer, the heat leaves the water, goes into the environment, being the freezer, and that's an exothermic process. When enough heat leaves, the molecules will freeze together. Okay. We're going to get to numerical values very soon. Understand that the energy required to make an element is 0. So one of the weirdest concepts, and we're actually going to talk about this really soon, so we're going to talk about it. One of the weirdest concepts and one of the most mistaught and misunderstood concepts is the idea that chemicals hold energy, or chemical bonds hold energy. When bonds break, they don't break on their own. They need to be forced to break. When bonds form, that they will do on their own. So it takes no energy to make an element. It gives off no energy to make an element. It's kind of like Legos. When I bought Legos in the 70s and 80s, even like the smallest parts had to be put together. But now they have just like a prefab piece. It's like, this whole piece is a motorcycle? Yeah, I guess so. So elements don't require any energy to make, so they have an enthalpy value of 0. Most things will have an enthalpy value of some negative number, meaning when they form, they release energy.
Yeah.
I'm going to revisit this later. Just understand, if you see an element, it has an enthalpy value of 0. And that means even the Brinkelhaus, the N2, the H2, and the O2, still 0. Because they're in the elemental form. Yeah.
Why does the universe favor low energy states?
Okay. It just does. So basically, there's a number of different ways to think about this. One way is whenever the universe came about, however it came about, it distributed its energy throughout the universe, and it's constantly harvesting that energy and getting it back. So a system that gives the energy back to the universe is going to be thermodynamically favored. Thermodynamics is the language of the universe. So if you have a process where that process releases heat back into the environment, that's going to be thermodynamically favored. That's a better explanation than it just is, right?
Yes, it is.
Okay. Moving on. Oh, other questions before we move on? Moving on. Okay. So here's a bunch of enthalpy types, and you're going to very quickly notice the pattern. But let's look at a few of these. When lava freezes solid, it's an exothermic process. Even lava? Yeah. When lava, which is very, very hot, freezes solid, it's still an exothermic process, just like it was an ice cube. Okay. Enthalpy of melting and enthalpy of freezing. This is just solid to liquid and liquid to solid. That's up to you.
It's kind of like,
Should we write it all down?
It's entirely up to you.
starts with the beginning of what's
The notes are online. You could write it if you want. You can skip it if you want. I don't care.
But is it important?
Everything's important, bro.
Everything's important, bro.
Life's important.
That's not my question.
The adult is up here talking. It's got to be important. Ian.
What's sublimation and deposition?
Excellent. We'll get there. Okay, so first of all, enthalpy of melting. Does melting require heat or release heat?
Release. Requires. It requires heat. Come on, guys.
Melting requires heat. Heat needs to go into a system for that ice cube to melt. So what is the sign of melting?
Delta and delta. XO.
plus delta?
Probably delta H melts.
It's
Okay.
delta plus
It's either going to be positive or negative.
positive delta.
If it's an
H.
exothermic system,
It's
it's
negative.
negative. If it's endothermic, it's going to be
Positive.
positive. So, does energy go into a system or release from a system during melting? It goes into it. So that's going to have a delta H that is
Positive.
positive. On the other hand,
Minus.
when something freezes,
Negative.
heat has to go out of a system, so the delta H is
Negative.
negative. Seeing how this works now? Okay. Enthalpy of vaporization is liquid to gas. When a liquid turns into a gas, does that require energy or does that give off energy?
Required.
Require.
It requires it. So that would be an positive or negative delta H.
Positive.
Negative.
Positive.
Positive.
If something requires energy, it's positive. Something requires energy, it has a positive delta H. On the other hand, condensation is when a liquid or a gas turns into a liquid, that's going to have a delta H that is what?
Negative.
And then sublimation and deposition. This is pretty cool. Sublimation and deposition is what dry ice does at normal pressures. Sublimation is going from a solid to a gas, skipping over the liquid phase. Actually, kind of going around the liquid phase. So sublimation is what the dry ice does at the bottom of the punch bowl. It goes right from a solid to a gas. So if something goes to a solid to a gas, is that going to require energy or is it going to give it out?
It's gonna require.
It's going to require it. That's why we put the dry ice at the bottom of the punch bowl, because it pulls heat from the punch and keeps the punch cold. So enthalpy of sublimation, positive or negative?
Positive.
Positive.
Wait, so
Yeah.
if it's a negative delta H, it releases energy, and positive requires energy?
Yes. And the trickiest part about thermodynamics, classically, is you have to think about the system. And because we tend to think of ourselves, we like to put ourselves into the system. You shouldn't do that. You're like, that thing feels hot. It must be absorbing energy. No, if it feels hot, it's releasing energy because you're the surroundings.
True.
True that. Okay, enthalpy of reaction is simply reactants to products. That could be positive or negative. We're going to calculate that later. So enthalpy of reaction is when the reactants become the products. Could be positive, could be negative. We're going to calculate it later. Enthalpy of formation is usually negative. There are a few things that are arbitrarily given positive values, but it's usually negative, again, because when things form, what happens? They release energy. Okay? When things form, they release energy. And I'll show you a diagram that explains that pretty well. And then enthalpy of solution
Plus.
could go either way. We have a really cool lab where some of the things dissolve and get hot, and some of the things dissolve and get cold. And then finally, enthalpy of combustion. I can't think of a single combustion that absorbs energy. Combustions, remember when you have a fuel plus oxygen makes carbon dioxide and water? So it usually goes kaboom.
So it's
What's the sign of a kaboom?
minus.
A sign of
What is the sign of a kaboom?
positive, negative.
Exothermic, so it's negative. Good. Okay. If you're ready to move forward, give me a thumbs up.
Wait.
If you have any questions, wave your hand around.
Wait, is it so if I experience doing Minecraft?
All right. Okay, so you learned about this. Okay, now sometimes you see the enthalpy number added to the front or the back of a reaction. In this case, it's an exothermic process. This is the combustion of glucose that you learned about in biology, cellular respiration.
Oh yeah.
Yeah, and when a mole of glucose reacts with 6 moles of oxygen, produces 6 moles of carbon dioxide, 6 moles of water, and 2,870 kilojoules of heat, which is a fat amount of heat. So that's an exothermic process. When the delta H is put on the product side, it's exothermic. On the other hand, if energy is required, the energy will find itself on the reactant side. So if I want to split water molecules into oxygen and hydrogen, I need to supply some energy. So that puts the energy on the reactant side, which means that delta H is going to be positive. Huh?
See.
One.
Do you see why this number is half this number?
Yeah, because there's two.
Yeah. 2 water molecule or 2 moles of water requires 572 kilojoules. That means to break down 1 mole of water, it's going to require 286 kilojoules. Seth, what do you got?
Why is it negative 287 instead of positive?
Who can answer that?
The reaction goes up.
Because it's an exothermic process. So energy is a product. So the system releases heat, therefore the delta H is negative. So it's energy is acting like a product. So the system's releasing heat. When you release heat, when the system releases heat, it's a negative delta H. Capiche? Verstehen? Comprende?
Comprende.
Comprende.
Okay. If you have any questions, wave your hand around. Now is a good time. If you're ready to move forward, give me a thumbs up. Close enough?
Wait.
Oh,
yes,
question.
Get a question.
Julian.
Solutions can be positive and negative.
Yes. We are going to find out later that when you dissolve something, it usually releases heat, but sometimes it absorbs it, depending on what you're dissolving. All right. Now, because heat can be treated like a product or a reactant, we can also do stoichiometry based on energy. So take a look. The question is simply this. How much energy is released when 340 grams of glucose is burned in excess oxygen? So just like any stoichiometry equation, or any stoichiometry exercise, we're going to start with a T-chart. Tough potatoes. What goes in this box here?
Nothing.
Nothing.
Not yet.
Only a single value is actually given to you in this exercise. And what is it? 340 grams. And I'm going to say glue because I don't want to keep writing C6H, those things. That's okay with you guys? Yeah, gotta go grams to moles. So I need to go grams of glue. Actually, now I'm just going to write down because this is important. Grams of C6H12O6 to 1 mole of C6H12O6. And where does a gram to mole come from?
The molar mass.
Yeah. Molar mass on the periodic table. So could you calculate the molar mass of glucose for me, please?
Probably pretty good because
There's a lot of stuff. But how big is it? That's important. It is big, but how big?
Probably fast.
If you do this job, you're going to get some money back. How much? A big amount. How much is a big amount?
You said
180.156.
that's what I got too. I got 180 pitch.
$1.80?
it's not a bougie. 180.2. It's not.
I got 180.
So 180 grams per mole for glucose?
Yeah.
Yay! Okay, now we would normally, when we're doing a chemical reaction from chemical to chemical, we would normally use the mole ratio. We kind of still are, only we're going to go from mole to heat energy. I'm going to look at that. What's the number in front of glucose?
6.
There's no number from
Glucose.
There's no number, so that number actually is a
1.
So 1 mole of C6H12, this doesn't take long at all, releases negative 2870 kilojoules. And we math it. And this will tell us how much energy, if everything was perfect, we're going to produce by burning our 340 grams of glucose. Do you have an answer or a question?
I have a question.
What?
What would cause us to get the number wrong? Besides wrong numbers, is there something that would
Just like every stoichiometry exercise, non-canceling your units. So this becomes this becomes this. And remember, you always start with a thing that has one number and no conversions.
But
That's
in a
conversion.
real life lab, how could this
Oh,
this be changed?
we're almost never able to capture all the energy. So remember your hot metal thing? The styrofoam container captured a lot of the energy, but not all of it. in the lab we're doing later on, a hot Cheetos lab, we're gonna burn Cheetos. We have to use a metal calorimeter, and metals lose a lot of heat. So because they're metal, they absorb a lot of heat. So because it's exothermic. Oh, some old dude wrote it in a book.
I don't always run out of food, but when I do, I get.
There's a way we're gonna calculate it, and that's actually the last thing we're doing today. But right now, some dude wrote it in a book.
I had.
That exact problem. How would I find it out?
It'll be given to you. There is a practice we're going to learn how to find that, but that's another time. Okay, so if I burn 340 grams of glucose, how much energy do I produce?
-5, 4, 2, 1.
What was it?
-5, 4, 2, 1.
Negative 5, 4, 2, 1.
0.1111.
5, 4, 2, 1. And the answer is kilojoules per mole. Kilojoules per mole of glucose.
How many moles do you have?
Well, see, that's the thing. It's that much energy, kilojoules per mole. So since we're dealing with a whole bunch, we can just go kilojoules. That's how much energy. KJ. Okay, now let's use the same process, but let's go backwards. There's your formula.
Energy is required to decompose.
Wait, didn't we already do this one? Oh, no.
Wait, required?
I'm waiting. That's the point. I'm going to wait while you do the exercise.
So why do we have that formula? Bam! What?
So all of the molecules that are already up there,
If I had a question like this, they'd want to be there.
Yeah. Some dude wrote them down, and we're going to take his word for it.
Wait, what do we start by dividing 572 by 2?
Yeah. I'm going to let you work that out.
Okay, I'll try.
Divide. Yeah, because there's 2 lives in there. Shut up.
And then we have to do water stain, which is 16.
And then another process.
It's like 18.
It's like a I gotta read that.
You found the last bar on the floor.
I did find it.
I got 74 kilograms.
Yeah. On my table. I think this won't go away.
Wouldn't you like to know, Weather Boy? 42 Branch, what you do?
I got 672.
I got 66.7.
What'd you get?
You don't have to divide by 2, you just do
What's the molar mass?
How do you not have this memorized?
Because
obviously,
How do you
how do you just solve it and then like do the math?
I have 0.
You just said something mean to me. I would like to report. Yeah, Mr. Pat God, yeah, Wesley's Mr. Pat God, Wesley is using his veggies. Oh, incinerate. Oh! You said roast me? Pat God roast him. Boy, he said I looked like I'm worked. I was just throwing off. Chicken bone, head.
Okay, so it sounds like you guys have the answer.
I have
Yeah.
675. Did I recall the head?
So let's see, if I was doing this, I would say I'm given 42.5 as my starting thing. Grams of water, grams of H2O. And I recognize that nothing goes there. Then I would put the grams of H2O here to cancel out the grams of H2O here. And I'm going to convert it to moles of H2O. And the periodic table tells me 1 mole of H2O has what mass? 18.0?
Ours looks the same.
Then I would look at that and I would say, oh, okay, so 2 moles of H2O is going to require 572 kilojoules. Now, if you made this 286 kilojoules to 1 mole of H2O, that's fine too.
That's what I
You're going to get the exact same thing. I just don't want to do any math until I'm at the
It
very,
goes to
very end.
667.
667?
66.7. Huh? 66.7. No.
Wow, that's kind of cool.
That's 674.
I got 675.
675?
Yeah.
675?
I got too.
I mean, now when you're
I don't
out.
know how you guys got that. Because I used. Where's your copy? I got Weston.
He's doing it on his fingers. Leave him alone.
4.2 is good.
Okay. If you are comfortable with what we did up here, give me a thumbs up.
17.
If any part of this is unclear, wave your hand around.
Just 17.
Mr. Vines, I got 17.
You're wrong. You know what? I think we can skip that. Okay. This is the single most important concept. This is the thing I told you. It's like frequently misunderstood, even mistaught. When bonds form, they attain a low energy state. Unbonded atoms are at a high energy state. So it's kind of like lonely people are at a high stress level, and if you find your best friend and hang out with them, you get to a low, hopefully, you get to a low stress level. Some of you are like, my friend always stresses me out. But hopefully,
Wait.
Yeah.
Unbonded state is high energy.
the unbonded state is high energy. Yeah. So
Okay, African child.
when you are, and again, and when I say, here's the crazy thing, when I say high energy, I mean 0. So we arbitrarily make an unbonded atom 0 units of energy. And when it bonds, it attains a low potential energy state, which chemicals like. They like a low potential energy state. So here in this little model, the unbonded hydrogen and chlorine are at 0. That's a unstable, thermodynamically unfavored system. But when they come and bond together, they get to a low potential energy state, and that's where they want to be. That's where the universe wants them to be. So breaking bonds is bringing them back up to 0. Forming bonds releases energy. Breaking bonds requires it. So if you are going to form or allow to form, you are going to allow to form the hydrogen-chlorine bond, it will release back to you 437 kilojoules.
What?
But if you want to break the hydrogen-chlorine bond, you're going to need to supply 431 kilojoules. And this is why when we're doing the enthalpy calculations very soon, most of our enthalpy numbers are negative, because compounds have a negative potential energy. They have acquired a low energy state. Yes, sir.
So unbonded have 0, so that means bonded have like negative?
Negative.
Oh, okay.
And that's just one of the weird things that chemistry does. We had to basically create an arbitrary value from which everything else is going to get measured. So we say an unbonded atom, 0 joules potential energy. Bonded, lower. So when that bond forms, it releases energy of this value. When we break the bond, it is going to require energy of this value. All right, how did I do?
Good.
Any questions?
Fantastic.
I know, right?
Fantastic.
Okay. More lingo. Oh, you were done? I'm sorry. You were still scribbling? It is. I think I uploaded this to Canvas. I think it's on Canvas.
What's the other thing you Steve? You said that.
Yep, it's on Canvas. So you can observe it on Canvas.
More water on Shanty's cup.
Let's not do that. Okay. Now, even the most. Oh, Seth, go ahead.
Sorry. So why does the curve go like this, and why not just keep going down? Like, why does it just suddenly go up past 0 at some point?
Oh, good question. So Seth asked, why does it just not go down to like 0 and just stop? Why does it go up again? Because the thing, are you paying attention? The thing that allows them to get to a low potential energy state is when the electrons of this atom are attracted to the nucleus of this atom. And the electrons of this atom are attracted to the nucleus of this atom. If you get them too close, then the electron cloud of this atom repels the electron cloud of this atom, and the nucleus of this atom repels the nucleus of this atom. So they get to a really good balance where they're not too close, not too far away, and that's their lowest potential energy state. If you keep getting closer and closer together, they start repelling each other and going back up the energy curve. That's what that means.
That's a good, no, that was a good analogy.
I'm
You want
glad
to
you
hear this
enjoyed it.
analogy?
Okay, moving on. So no matter how exothermic a process is, it's always going to have some barrier to it going. When you take chemistry AP, you learn about the kinetic barrier, what we call the activation energy, and we'll talk about a whole bunch of mechanisms and stuff. But right now, just realize that in order to begin a reaction, you have to overcome the energy barrier. And the energy required to overcome the energy barrier is called the activation energy. So the bump, all reactions have them, is called the energy barrier. And the energy to overcome the energy barrier is the activation energy. You probably heard about catalysts before. A catalyst is something that speeds the reaction up. And it does that by reducing the size of the hump. A catalyst basically creates a shortcut. So instead of going all the way around the mountain, we're just going to blow a hole right through the mountain and make a shortcut. So a catalyst basically makes a much smaller energy barrier, so it requires less activation energy. Okay. The delta H of a reaction, I said, could be positive or negative, right?
Yeah. Of a reaction?
Of a reaction. So in this case, this is an exothermic pathway because the reactants are higher energy than the products. Let's say the products are at 20 and the reactants are at 50. Final minus initial, 20 minus 50 gives you a delta H that is negative 30. So in exothermic. In an exothermic process, the energy of the system drops, and the amount it drops, that's the energy it releases. Okay? Does that make sense? So in an exothermic process, the energy of the system drops, and the amount it drops from its original value is the delta H of the reaction. It's how much energy is released. If you understand that, scribble on your notes or on your friend's hand what an endothermic pathway would look like. Yeah.
Could you explain the exothermic one more time, please?
Sorry, what?
Could you explain the exothermic one more time, please?
In an exothermic process, the reactants are at a higher energy state, and they go to a lower energy state. And the difference between where they ended and where they started is the energy they give off to the environment.
And is there an energy barrier in an endothermic reaction as well?
Yep. All reactions have an energy barrier. Sometimes it is weak, sometimes it's not so weak. Or have you scribbled on your paper or on your neighbor what an endothermic process would look like?
Wait, Endothermic process?
Yep.
Can you explain
It
it?
would be like that, but like flipped over.
Oh, it'd be that, but the opposite, because it has to
Gain energy.
gain the energy.
Yeah, pretty much.
Okay.
Yeah. So yeah, if you drew this backwards, whoop, that would be an endothermic process. Or you could say, I'm starting with the reactants, I'm going up my energy barrier, and then I'm ending up here. And that's going to be my products. And this delta H was going to be positive because the reactants have gained energy. So in an endothermic process, your products are going to be above the reactants. Yes.
So.
Okay. If that is clear to you, give me a thumbs up.
Yes. Wait, but let me write this real quick.
All right. I do not know why plan so much work today.
I go way further than I was supposed to go.
Yes.
Hot metal calorimetry.
Oh yeah, way further than I was supposed to.
Hey, we're cooking though.
That's fine.
Uh-oh. Oh, sorry.
This is a good place to stop. I think the next one is math. So let's see.
No.
Oh no, not the math. Oh no.
It's fine. The assignment's looking short.
Oh yeah. The next part's Hess's law, so that's fine. Okay, so this is a good place to stop. The worksheet that unlocks tonight is the worksheet I need you to do over the next 2 days because we have a lab Tuesday, Wednesday. So don't be like, no, I have to do it all at once, because you won't have an additional worksheet Tuesday and Wednesday. Does that make sense?
No.
A lab worksheet just unlocked today.
Okay.
It's marked due tomorrow,
Okay.
and you can do it over the next 2 days because we're going to be in a lab lighting Cheetos on fire
Okay.
Tuesday and Wednesday.
Okay.
We're gonna have real flaming hot Cheetos.
We're gonna have real flaming hot Cheetos, exactly.
Hey, bring that one up top, young blood.